Right, welcome back. You've now got through the first part of your accreditation program, which was module number 1. Let's just go to the right page. So module number 1, you've just finished the introduction to Janssen AG as a company, and you should have a good overall idea of where they're situated, how their local markets operate, and what kind of business they have, and even how the products are manufactured. The next part you're going to be doing is a very important one for metalworkers in South Africa. And hopefully you can use this to convince architects why steel is so important. And there's a session now, part 2 of module 1 on why steel. And after that comes module 2, part 3, which will be DocuCenter. And then we'll catch up closer to the time. All right, enjoy.
Okay. First slide shows the Nest, one of the stadiums in China, in Beijing, which was made entirely out of steel. And here you see that this construction was only possible to be produced in steel. And it shows the strength of the material and the possibilities you have. Nicely and nicely for us, the building was equipped with a lot of Janssen elements. It was designed by a Swiss architect office. Here you see the tonnage of material that was used for the construction. And here very soon, yeah, it is huge. It is, well, it was done for the what was it? The year 2000? I don't even remember what year it was for the Olympics.
I thought that was concrete. It was for the Olympics in 2018.
2018.
Yes. Okay.
So this is it. And the inside, the fire protection elements, doors, and sections of the facades were made out of Janssen steel elements. So again, steel to steel, steel and concrete and glass was the material used here. I think we will see now. We don't see really the numbers for Janssen, but there is a significant number of doors. I think some, I don't know, what was it, 300 doors or some, fire stop elements, and the facade. So different systems that contributed to this nice steel building. So sometimes steel is the only way to go when it comes to statics. When it comes to sizes, you will actually end up with steel as the only solution oftentimes. What other advantages does steel bring? When you look at the optics, when you talk to architects, they care a lot about optics. Here you see the joints. The joints are different. The way you join profiles on steel profiles and aluminum profiles is different, and it also gives you a different appearance of the end product. You see that here, the mitred joint on the steel, they are welded. You cut the profiles always at well, not always, but most of the times at 45 degrees. You weld them together, you grind the welding seam off, and you finish it so that you don't see any grinding patterns, any let's say distortions of the surface. So in the end, you get a uniform surface. In aluminum, this is not the case. Look, you know that. These are basically plug elements, right? You have the corner connectors, and you're left with these lines here. So sometimes this will make a difference. Architects don't like them sometimes, and with time they may actually open up. These gaps may become greater and lead to the distortion of the whole element.
Something else, Andreas, in some instances, those are what I call dry joints, although the aluminium factories do put wet seal there. Mm-hmm. But because the wet seal, it's not a very easy joint to seal, because you kind of work with the thickness of the material or seal behind. Mm-hmm. So they become what is not truly called dry joints, but sometimes on high pressure buildings where you have maybe 2.5 kilopascals of wind load and pumping wind load and rain, mm-hmm. Those dry joints can become a problem.
Wow, okay. Oh.
Yeah,
good to know.
You were saying earlier about that beautiful building, Kristiansand, was it? And I think you mentioned a wind pressure there in Norway of 1.5. And here in Cape Town, we've done a couple of large buildings, one of them at 3.8 kPa.
Oh, wow,
and,
okay.
On the unitized facades, those joints are not a problem. But on shop front type systems, they are a problem.
Okay.
So
Okay.
have the steel, and this is a great image to show the difference.
Yeah, and in Cape Town, the water really actually gets sucked into the building. It's like it really here it rains sideways. So it's the waterproofing aspect I feel is as strong as the visual aspect as well.
Wow. Okay. Well, thank you for that. That's yet another reason that I never thought about. But yeah, it makes perfect sense. I only see these, older aluminum doors, how they open up. These gaps just look ugly, and yeah, I imagine they are not tight at all.
Agreed.
Okay, another reason or another advantage of the connection method of steel profiles is the fact that, or actually not the connection method. It is the connection method on one hand, but also the stability of the profile or the statical resistance is the fact that you can use less material. You don't have to use, for example, here the middle profile as in aluminum. Oftentimes you save the width of the face width of the profiles. And the most slender, the thinnest profiles are made out of steel. So that's yet another reason why steel is the preferred material to go with. Here we have a comparison, direct comparison, two systems that we carry in our portfolio that we sell parallel to each other. But here you see the comparison. The same values, the same statistical values, and with steel you can save 35% of the face width. Right-hand side is aluminum and left is steel. Aluminum, by the way, is 3 times softer than steel and therefore requires more material to carry the same loads, the same type of loads. Sharp edges. Sharp edges is a topic that we are all often confronted with, or we get the questions. Look, you mentioned that aluminum is extruded, so you can produce very sharp edges, and usually this is how it's done. When you bend steel, so especially in the rolling process, the edges stay round on purpose, actually. And there is several reasons why we do that. Well, theoretically, we could also produce sharp-edged steel profiles, but we don't do it, and the reason is shown here. When you coat the steel with either wet paint or powder paint, you have to guarantee a certain radius of the edges. If you don't have it, then you may have the so-called, what is it called, the coating, the fleeing coating, or they call it, where you get actually exposed edges of the material when the radius is too small. On round radia, it is much easier, and the coating stays much better. This is actually the way we do it. The rounded edge. This is the production method that we use, or the edges that come out of our production process. This sharp-edged sharp edging issue is okay. Hello. Somehow we lost the connection. Dave, I see you're in, but I can't hear you, and I can't see you guys.
Can you hear us now?
I can hear you now, and I can see you now.
Okay.
Was it on my side? Did I press something, or was it just an interruption?
I don't know whose side it was.
Okay.
Sure.
Okay.
Yeah.
Just deteriorated. The last thing that we saw was the opening of your slide with the steel profiles on the left and the aluminium profiles on the right.
Okay. Okay, then let me go back.
The 110 and the 140 base.
Okay, that one. All right, good. So clear here, with steel you can save the face width, you can produce much more slender profiles. The construction in the end offers you much more glass surface and less profile view. Here, 2 profiles that we carry in our portfolio. We sell them. Yes?
We can't see your screen. You're not sharing it?
Oh, I am in fact, but okay, let's do it again.
We don't even see you.
Okay, there we see you now.
We see you.
And I will show you the... How about now?
It's coming.
Yeah,
Very good.
perfect.
Okay.
No. Yes.
Okay, you see the 2 profiles? Okay.
Yes.
Okay, so the story again, comparing 2 profiles that have the same statical values in aluminum and steel, you see that the steel solution offers you a 30% less phase view of the profile, and therefore more, of course, more glass surface. So huge advantage of steel. The slimmest profiles are made out of steel. I mean, it's logical. Aluminum is 3 times softer than steel, and therefore you can use, or you have to use much more material on the aluminum systems than on steel. And if you want to reinforce aluminum systems, you will also use steel. So steel is something you can't avoid in construction oftentimes.
Yeah.
Let's talk about the edges. The edges of the profiles, well, look, on aluminum profiles, the edges are sharp. This is due to the extrusion process. The matrix can be designed in the way you want, and so the sharp edges are usually the result of the extrusion. On the steel profiles, in the rolling process, the edges stay round. You bend the steel, you bend the strip metal, and it stays round. Is it good? Is it bad? Well, it offers some advantages, in fact, these round edges. The question is, can you also produce sharp edges on steel profiles? You can, but it does not really make much sense. And this slide shows you why. When you coat a profile, applying a wet paint or a powder paint, you have to make sure that it sticks to the surface. And if you apply it on sharp surfaces or sharp edges, you may get spots where, with time, the coating will disappear. It may get damaged, and it can also lead to injuries. These sharp edges and profiles sometimes are not desired, and in fact, they are prohibited in some public buildings. I will show you where. What we apply here, or what we produce here at Janssen, are these type of round edges with a minimum radius of 2 millimeters, which are good for all public buildings. And this regulation is a legal one. For example, school buildings in Europe cannot have, let's say, construction elements with sharp edges to the height of 2 meters, so where it's reachable with a child's hand. So the regulation, I think you will see here, it comes from a German insurance organization, and they actually say, can you still hear me?
Yeah, yes.
They say you have to have edges of at least 2 millimeters of radius on facades, windows, and doors to prevent injuries. Kids running against a short profile or touching it unintentionally, this may lead to injuries. So therefore, we are happy with the round edges, and there is advantages of this. Yeah, we can get into all the public buildings. Oftentimes, we can't employ the aluminum systems due to the sharp edges. We have to go for steel. Okay,
There's something, Andreas, from the aluminium side. I know when developing dies to create profile suite.
I lost you, Dave, now. I lost you guys again. I can't hear you. I can hear you now. Okay, I will turn off my camera. So maybe this will help. I can't hear you guys. I lost you. I can't hear you still. I don't know. Shall we try again? Just rejoin the conference. Well, let's try again. I'll rejoin.
Camera doesn't matter. So let's do this. Do you want to use your phone as a hotspot?
Andreas, can you hear us?
Yeah, I can hear you now.
You might be muted.
Am I muted? No. I am not muted. I am. Yeah, my phone is on, my camera is on. Can you hear me?
So Andreas, I've turned my camera on.
Yeah.
Let me just see. Maybe it's another reason. Just give me a second. No. Andreas, can you hear again?
I can hear you, yeah.
Okay, cool. So I'm not sure if it's my side or yours. So what I'm going to do is our Wi-Fi router is a bit. I'm going to move it closer to our Wi-Fi router and see if that helps.
Okay, and I will turn off my camera. Maybe this will also help the.
Yeah, I think I know that in the past with Jerry and then we also sometimes had a bit of a call drop. I'll put our camera off as well, and then Luke's just gone to fetch my my power supply just to make sure that there's no drop in processing power.
Okay. Okay, so shall I still wait till Luke is back?
Yes, I'll mention what I was saying to you earlier on the aluminium side.
Oh yeah.
The guys for the tool steel to create the dies, what you're calling the matrix, those dies you can't actually have a sharp edge on the dies because it ruins the extrusion. So typically when they're creating those die designs, they work with a radius of about 2. So I think you probably find that a lot of the aluminium guys are most likely moving towards more of a radius. I don't know what Schuko's doing. Are their profiles, do they have a rounder edge?
I see the sharp edges pretty much everywhere across the whole line. But I will have a closer look now that you say that.
The wire that cuts the die is 0.3, so that's one of the more common radiuses, at least on the inside of a profile.
So Luke's just saying that
inside corners.
Okay, on the inside. Yeah, okay. So I know that on the large dies, the guys were using a minimum radius of 2 millimeters because otherwise, because they can also burst dies. I don't know the technicalities of it, but when you go for the larger profiles and the thicker walls, they actually try and ensure it's 2 millimeters. So it's something I can look up.
But even in any case, when you powder coat it anyways, you lose the sharpness of that corner.
No, it doesn't. What Andreas says, it's actually a problem for powder coating because what happens is you end up with a very thin coat on that edge. It's a typical painting problem.
Okay.
And it's a problem for both powder coating and for wet application. So that you end up, the sharper the edge, the worse your coverage.
But does it also occur on aluminum profiles when you, let's say, powder coat them and they have the sharp edges? Will you have this problem on the edge?
Look, it's worse for wet spray because you don't have electrically charged particles. Because you have electrically charged particles, it's not as bad on the powder coating.
Okay, but in general, okay. Then
but I think so your main point is that the aluminium typically is sharper, and we're on that point. So we fully agree.
That's it. Yeah, it may be changing now, but still, this is the argument that sometimes, gets us the projects or makes us or allows us to win a project against aluminum in public buildings. This is still the case here.
Excellent. Okay.
And as I said, this is regulated by the law. It's not our invention. It's a prerequisite for public projects, oftentimes schools, kindergartens, and so on.
Excellent.
Okay, then let's talk about the stability. Weight. Weight is the first one. Well, we have a comparison here to show you the difference in weight of aluminum systems and steel systems. For that, we used a flat steel of 20 by 10 millimeters, and the length is, I think, 1 meter or so. Yeah, that's the dimension of the flat steel. Let's look at the weight. Aluminum weighs 0.54 kilograms per running meter of this type of flat steel. Let us look at steel. Well, steel is 3 times heavier, 1.5. So theoretically, the steel profiles will be 3 times heavier if you compare them 1 to 1. But that's really not a fair comparison. Here again, the weight, again, you can see it. It's the steel flat has 0.9, 0.3 kilograms. So exactly 1/3. Yeah, the steel is 3 times heavier. But let's look at statics, and let's look at the final product that allows us to carry the weight in the end. Moment of inertia. This is important. This is the statical value of the profiles, the IY and IX values. For aluminum, you see them here. For steel, they are seemingly the same because they do not consider the material. So in the tables, in the statical tables, under each, let's say, profile you will find in a catalog, you will have this table, the values, IY, IX, and WI and WX. They do not consider the material. So if you want to achieve the same value for aluminum and steel, you would have to actually do the multiplication of the let's say material of aluminum to carry the same load. And this is my predecessor Urs, who was weighing at that time 120 kilograms. He steps on the aluminum bar, deforms it. The formation stays. It will not come back to its initial form. And the same trial with steel, just to show you the difference. The steel bar, same cross section, the same IX and IY values. Again, not considering the material, but look at the result. Of course, steel will hold these would hold his weight, 120 kilograms, no deformation, and this shows the difference between these two materials. This, of course, this translates to the statical capabilities of the profile. So, aluminum is 3 times lighter compared to steel, but also 3 times softer. This is clear, I guess, if you guys had some physics in school. This is pretty easy to understand. This translates to the fact that we have to use more material on the aluminum systems than on steel. And this, again, translates into the depth of the profiles that can be used. So same IX values, but you will see that the dimension of the profiles are different in the end.
Yeah.
So you will just have deeper profiles on aluminum. That's the tendency always than on steel. Inside, and this was the outside. This is the inside side. So both let's say sides of the facade in this case will show the same characteristics. Does it matter? Well, you may say, okay, it's really just a couple of centimeters, but it does matter. This depth of profiles does matter when it comes, for example, to large facades where you have air circulation, where the facade is the outer skin of the building, and especially in buildings that have increased hygienic requirements. Can you still hear me?
Yes.
Okay.
All good.
So hospitals, and especially in these days when hospitals are, let's say, our main point of interest or important buildings in our society, this is where it may actually play a role. And the reason is, with the deep profiles, you may get some air distortion, air circulating alongside of the facade, on the inside of the facade, may actually get into turbulences. You may get some accumulation of humidity and some growth of molds, accumulation of bacteria, which is not desirable. If you use a thinner profile, this effect will be much less. and you will have a better circulation of air. Oftentimes in hospitals, this is a reason why steel is chosen as the material, because of the depth of the profile. So one more reason, the aesthetic reason is one, but also the hygienic reason.
Very interesting. And on the aesthetic side, the architects have often spoken to us about where we've got tall spans in aluminium, and you end up with a large box section of maybe 300 millimeters deep. And although it works, the architects don't really like it because it takes away from your transparency. So if you stand it obliquely, so if you straight on, it's fine, but as soon as you oblique, it kind of cuts out quite a lot of the plate.
Yeah, the trend is always to reduce the face width and the depth of the profiles. This is a let's say global trend everywhere.
Less is more.
Exactly. Our partner Schüco delivered us a good example why they actually confirmed this argument. When they built their headquarters, they used a steel facade instead of aluminum, because they were not able to really cross or let's say to cover the whole span of the facade. This is a huge one. You had here, well, let's see, this is just the size of the elements, 10 by almost 3 meters. These are the elements. You also have some requirements on the wind load, the bending of the system. So they went with steel instead of their own system, and not only the standard profiles, but they used the extra profiles, the standard or the personalized profiles from Janssen. On several projects or many projects, you hit the let's say a point where aluminum will be out of question, and the standard steel profiles also. But thanks God, we offered the line of extra profiles, so strengthened profiles with thicker walls, individually designed for the project, for the purpose, and these profiles do magic. I mean, they are responsible for the nicest projects we have realized.
Beautiful.
So this is the building. This is the cross section. What was used here, as you see, the personalized profiles. The rest of the structure is standard. This type of construction of facade is also called the FIS basic facade. Here you do not take the profile from Janssen, not the FIS profile, but any profile, and the connection to the ground construction is either welded or bolted, instead of just a plug and play like you would have it on the FIS profile, which I will show you later on. Okay, so far so good?
Yes, thank you.
Okay, then let's move on. Insulation. Insulation is also one of the reasons why we recommend steel, and this can be explained in with physical, let's say, or physics in the end. Let's look at thermal conductivity. When you compare aluminum to steel, you will see that steel has a better insulating properties than aluminum. Aluminum will conduct heat 3 times faster or better than steel. Here, by the way, we have the melting temperature comparison of the two materials, and this translates to better, or let's say to better insulation when it comes on to steel profiles. Here, the example, the real life example, we have a heat gun here, 400 degrees. It's pointed at the end of the same steel bar you saw in the beginning of this presentation, where it was just stepped on. Here we turn it on, and we measure the temperature on the other side of the steel flat after, I guess, a couple of minutes. And this will actually prove that aluminum has or translates or transmits the heat much better, much faster, and is, let's say, the worst material when it comes to profile or window door construction.
Yeah.
Okay, okay, this one is running as well. Now measuring the temperature. You see here 23.4 on steel and 27. So the experiment confirms what physics tell us. And this again translates to the thermal values of steel windows versus aluminum windows. Steel is a better insulator than aluminum.
Yeah.
Yeah, okay, this runs again, another comparison of temperatures, still 23.4, and here 32. So here we don't have any transfer of heat anymore, and here it still continues. So aluminum will conduct much better. I'd say even 3 times as better, as good as steel. Okay.
Does that the fact that when you make your window out of steel, it being a thinner thickness than the aluminium, would that further improve the fact that it conducts less because the material itself is thinner?
That is a fact. Yes, it will have an effect on that, and it will also have an effect of the thermal values of the entire element. The more glass you have, the less the let's say the proportion of steel or aluminum on a window or a door, the better the thermal values of the whole element. So yes and yes, yeah.
Just comes together.
Mm-hmm. Yeah. The
knock-on effect.
It will have a positive effect. Yeah. Okay. So here you see the results of the experiment. The curves, the temperature curves of both flats. So definitely, I mean, this is the proof that it's not only a marketing gag, but it is a fact, physical fact. Aluminum is a, let's say, better transmitter of heat.
Yeah.
Fire resistance. We often produce fire stop elements out of aluminum and steel. Let's see how it compares. Well, the melting temperature tells its own story. Here it's quite obvious. Aluminum will melt much sooner in a case of fire. Here you have the two curves. Aluminum 660. This is the melting point. 1,500. It's not even on the scale for steel. And here you have the temperature curve that is reached usually during a fire stop test. So you will be always, just after a couple of minutes, above the melting point of aluminum. Steel will have much better chances of surviving, and therefore also does not need to be reinforced or protected as much as aluminum. Yeah. So again, here a movie. This is. Can you hear the voiceover or the sound? Yeah. Okay. It's okay. It's just music. This is a movie shot at the EFT Rosenheim, which was in the past our testing facility where we tested the elements. And here you see how a fire stop test is performed. Left-hand side steel system, Yanisol 2, and a right-hand aluminum system. So basically, what happens here? You have a fire chamber where the temperatures can reach up to 1,200 degrees. And then you measure the temperature on the outside of the element. As you see, there is different sensors at different points. They're all defined by the norm, the testing norm. The temperature is not so bad to the 360 degrees. Forward it a little bit. I guess this is just to demonstrate the forces or the heat that is applied to the elements. As you see here on the right-hand side, nicely visible the what do you say? The intransparent color of the glass. Insulated glasses, of course, they have several layers of glass. In between, you have a cooling gel which activates and evaporates and cools the whole element. The result is this lack of transparency and this opaque color or matte color of the glasses. So just to summarize it, better properties of steel when it comes to fire protection, higher melting temperature. Here an example of a handle, aluminum handle after 10 minutes. So you see it's not there anymore. Steel will be untouched yet. During the fire resistance test and also during a case of fire in a building, the elements are exposed to heat and to deformation, therefore. Well, thermal expansion leads to deformation of the element, and you see that here quite nicely. This is a 2.5 meter door, a double wing door. And during the test, this is probably the highest temperature reached now. The element is pulled towards the fire. It just expands more on the fire side than on the cool side, and you have this bending. In this case, this is 18 centimeters in the middle. And to prevent the door from opening and prevent gaps from opening up, you have to protect every fire stop element with a couple of, let's say, measures. One of the measure is a bolt on the hinge side. I have actually later a more detailed slide that explains these elements that we have to pay attention to. But it's basically a bolt on the hinge side to protect the opening of the door here on the hinge side. An additional locking point to the top, usually, to protect the let's say the corner of the door. You have to use all steel elements, so no plastic, ideally no aluminum elements also here when it comes to fittings. And you have to pay attention to the type of glass, of course, and the joints that you produce. We will speak later about these detailed elements that need to be paid attention to. I have another fire stop presentation for you. But all in all, again, to summarize it, steel, as the more resistant material, will withstand a fire much better than aluminum. So yet another reason for steel. Steel is super strong, as I said, 3 times stronger, harder, and more resilient than aluminum. This translates also to the number of hinges and the weight of a door leaf or window leaf. For that case, here you have an example of a double leaf door made out of steel profiles. If you just look at the hinge table, for this type of door, you would be able to use 2 hinges only on each side, and the maximum weight of a leaf can be up to 230 kilos. That's quite considerable, especially if you think that, again, this will be one statics, and the second will be the visibility or the aesthetics of the door. 2 hinges, of course, look better than 5 hinges, like you would have on the aluminum door. Direct comparison to the same size of door. What does aluminum system allow us? Well, it will allow us 150 kilos of maximum weight, and for this door you would have to use 5 hinges. 5 hinges looks kind of dumb on a door. That's one thing. The other thing is you have to adjust them. You have to lubricate them. Parallel adjustment of 5 hinges is more difficult than adjustment of 2 hinges only. So again, advantages on the steel side. Okay?
Yeah.
Clear. Okay. Good. Expansion, we touched upon that as well already. Expansion is greater on the aluminum side. Aluminum expands twice as much as steel. You have here the expansion coefficient per 10 degrees Celsius and 1 meter of length. This again translates to, of course, deformation of the door or a window made out of these 2 different materials. To visualize it even more, to make it even more pronounced, let's have a look at the temperature of a door or window that is exposed to sunlight. We did a little experiment here on a sunny Swiss day, 21 degrees, I guess, and we measured the temperature of 3 different car colors, the white car, silver car, and a black one. And this is the temperatures that we measured. Surface temperature of the white car was close to 40 degrees, outside temperature 21. Surface temperature of the gray, more than 41, and the black one, more than 60, or almost close to 65. And now tell me, what is the common color of windows and doors in steel and aluminum?
Black.
Is it-
Black
it's
okay.
dark. Yeah, it will be black. It will be anthracite. So we are rather on the, let's say, darker side and higher temperatures. So expansion is a topic here, and again here to demonstrate the expansion coefficients. Steel, roughly half the expansion coefficient of aluminum, and pretty much in line with glass and concrete. Since we combine these three materials, having the same expansion coefficient, of course, will make the elements much more controllable. Let's say the expansion in the same manner will help, let's say, stay in the shape of the whole element. Aluminum,
yeah, more compatible.
exactly. Aluminum needs some more, let's say, tolerances in general.
Yeah.
So does that mean? Is the expansion coefficient low enough that you actually don't need expansion joints?
That's right. On facade, for example, and this will be my next slide, you don't need that, or the system, the way it is designed, takes care of the expansion already. Yeah. I am not sure how you manage it actually with the connection to the building or to the sides. There may be some measures in this case, for example, 130 by 19 meters. But from what I know, it is much easier to control the expansion of a steel facade than an aluminum. There may be some expansion gaps or joints that you need to incorporate on the steel facade, but they will be considerably smaller than an aluminum. Yeah, and this is the argument here.
I think just for your info, the aluminium systems that are unitized, each unit has expansion ability or tolerance built in on the verticals, on the mullions, and then on the sills and the gutters, or the heads and the gutters. So each element then has enough expansion to deal with the expansion of the aluminium in each unit. On the systems that are not unitized, like the stick systems, which were the most common in the old world, the stick systems controlling the vertical expansion of aluminium, you have a gravity bracket at the bottom of the main stick, and that the rest of the vertical stick or mullion is then only wind load brackets, so that you don't hold or you don't create fixity in the vertical direction. And then I think the one area that probably does have some impact, and I can't answer technically, is if you have 130 meters in the lateral direction, in the width, there will be some impact on those systems. So the transoms typically have some give, between the transom and the mullion on the inside, and on the outside, the glass has some give because each of them are embedded in silicone. Although it might be held mechanically, there's normally a little bit of allowance. So it's not just taken up in the material. It's the joints is where the secret lies. But definitely the stick system, in this example, a unitized system will handle that much better than a stick in aluminium.
Okay. Yeah, so this is it. Thank you, David. Well, I have to say, I'm also learning from you. I mean, Dave, you have so much experience that, well, again, adds to my portfolio of arguments. Thank you.
It's good. It's good to know.
All right. Okay, so here we have it. Facade is one thing, but doors, double leaf doors, is another thing where this may play a role, and especially if you have panic doors, escape doors. You have to make sure that the door always opens, so there is no gaps that close when you have, let's say, strong sun radiation. And the example you see here, standard door, we have the temperature difference of the outside temperature and the sunlight. So here you have 60 degrees on the surface and 5 degrees air temperature. This will lead to a thermal deformation and thermal expansion and will result in a smaller gap between the two leaves. Standard-wise, we have a 5 mm gap between the two leaves, but when you consider now the expansion, this gap will reduce on aluminum by 3.15 mm, and on steel will also be reduced, but to, let's say, a much lesser extent, roughly factor 0.5. That means that panic doors, escape doors are much likely to open it in any case, even if they're exposed to sunlight, if they're made out of steel, than aluminum. Yeah. Clear? Understandable?
Yeah.
Makes sense. Okay.
Good.
And we actually have, this is pretty strict, it's a strict regulation when it comes to panic doors here. This ability to release, as it is called here in Europe, is a must for an escape door or a fire/escape door always. Yeah. So again, steel gives us an advantage here. Especially in places like this, so huge differences between the air temperature and the surface temperature of the elements, this may play a role. This is why, you know, in the mountains we see a lot of steel, very little aluminum. It has to do with the expansion of the material. When you come to Switzerland, I'll take you to this place and demonstrate it in real life.
Brilliant.
Okay, let's talk about the variety of materials or different types of steels and aluminum. Well, aluminum we have extruded, and that's it basically. So natural color is always gray. You can coat it, but if you want to keep the alloxated aluminum, you will be stuck. You will be, let's say, bound to one color. When it comes to steel, we offer here in this case of Arte, Arte 2.0. We offer different variants of steel. We have the galvanized steel, we have stainless steel. In some systems, we have two types of stainless steel. And in the case of Arte 2.0, we also have the Corten steel, which is a weather-resistant non-stainless steel. So it will rust, it will build a oxidation layer, but this layer will protect the rest of the material from rusting through, from oxidating all the way.
Yeah.
I don't know. Do you guys have a sample of the Corten steel?
It's not used that. No, we don't. For the Janssen stuff, we don't. And I saw it in your workshop, which was beautiful.
Okay.
Locally, the guys are not using it that much because the Corten as a brand name is quite expensive. There are some alternatives, but I don't think they have the same quality as Corten.
Yeah, I think in the meantime you can even get paints that resemble a oxidized surface. That's one. That's true. And I have to say it's rather a fashion these days. This Corten steel does not offer many advantages. It just looks cool, but it may also lead to troubles.
In fact, the building that we've got the showroom in, Andreas, has got, I think they made a decision not to pay the extra price for the Corten, so now we've got rusted steel plates outside. I don't know if it's painted or if it's rusting. It doesn't have the same effect.
Okay. Well, that sometimes you may hit this problem also on Corten. An example would be a white facade and the Corten window on the outside. It's really not a good idea when it's exposed to rain, to weather. You may get these. So pluses and minuses, but it's an interesting material, and you just can't do it in aluminum. These effects you cannot achieve with aluminum. Right, let's look at energy consumption or the energy efficiency of the material itself. And for that, to show that, we have actually accessed one of the a institute that measures the efficiency of production processes, and we had a look at the energy needed to produce 1 kilogram of a material. This is what we got as a result. And as you see, aluminum needs considerably more energy than steel to produce a 1 kilogram of this material. The factor is, if I'm not mistaken, let's say 1, 2, 3, 4, 5, more or less. So factor 5. So this translates to not only higher prices, well, higher prices included in the material, so the process energy is also part of the final price, but also just the environmental impact. It's much better, let's say, lesser than on the steel side than on the aluminum side.
Andreas, question?
Yes?
The steel, just that I understand this graph properly, the material energy consumption, I take it because steel is in the form of iron ore, it comes ready, no energy required. Is that what it means?
Correct, correct. Yeah.
Okay, whereas aluminium has to go through a smelter.
Right.
Okay.
And more, I guess, just more energy, more processing steps need to be included in the aluminum production.
Yeah, the exploration,
Also, what I understand is if you use recycled aluminum, and oftentimes it's done this way, so you mix the let's say the ore or the aluminum, what is it called, the bauxite, bauxite,
Yeah.
and recycled aluminum, and that requires even more energy input because the recycling of aluminum is much more elaborate than recycling of steel. Steel you can recycle without any loss of quality, and aluminum does not allow that.
Oh, okay. Yeah, I see the process energy consumption, I understand. So I just did that material energy. I was wondering if it's embodied carbon or what does it actually mean?
This will be, I think, let me see if this is described here on the previous slide. I think, was it here? For material, which are also energy carriers, petroleum, material-based energy requirement. Okay, this is how they defined it.
Okay. So just let me read that again, which are also energy carriers. Okay, petroleum, I understand, also taking into account as a material-based energy requirement. Okay, I'll look at it again. I'm understanding it a bit, but I'll look at it again.
Yeah, but it is the material-bound energy somehow. Yeah. All in all, we are better on the steel side than aluminum.
Yeah, there's no doubt. It's amazing.
So this is it. Yeah, and then if you, for example, work with steels, I know this translated to the, let's say, energy consumption of a meter or a kilogram of a well, actually it's a meter, a running meter of a profile. Then again, you will get this factor even higher. It's like 8 or 7 here. So I guess transforming aluminum, raw aluminum to profiles still will require more energy. Beforehand, on the previous slide, we only talked about the raw material. And now if you extrude it, then again, it will even require more energy because you have to heat it up to the melting point and then extrude it. Steel, you can pull or roll in a cold state.
Do you have the source information for some of these? Because this is a topic that I'm actually very invested in.
Yeah, this comes actually. This is the source of it. Hunold and Knoop. It's actually. I'm sorry. I have to correct myself. This is actually a plastics production company. They produce plastic and I think other materials which they combine with plastic. So they issued this comparison.
Okay. Mm-hmm. No, that's cool. No, this is a question that I've asked myself for many months during my last year of studies. Steel versus aluminium in terms of an embodied energy. You know what it takes to make the material and what it takes to turn it into a window. Yeah, it's nice to finally have an answer.
Yeah. This is it. I was actually surprised how big the difference is, but it makes sense because aluminum, it's one of the let's say has the biggest CO2 impact of all materials that we use in construction.
Yeah.
Okay.
I'm quite surprised by glass because there's a lot of energy in those furnaces. You know, at the in the glass float plant. Mm-hmm. You know, those are massive furnaces that run 24/7, 365. You can't turn them off.
I don't remember it's kilo for kilo, so it's for a kilo of glass.
Yeah, you're right. You're right. I'm also thinking about this because this goes well above 1,000 degrees.
Kilo glass probably a lot more.
Maybe it's more. Okay, let's not take it. Let's take it with a pinch of salt.
Yeah. We carry on. I think we take the point, but we got lost in the detail. Back on the page. Let's go.
All right. Okay. Good. So profiles again, same thing. More impressive is the longevity or the resistance of the materials. Here you have a steel door which has been in use for 32 years and has more than 1.6 million cycles. This is a entrance door to a university in Essen in Germany. So highly frequented door, but you see it's still it's still in its original design. 3 hinges, but basically all the parts are still there. All the connections are intact. Just the mold is growing on it, but that's really it. The material is still intact. Same building, an aluminum door. That's to say, another entrance door done in aluminum. Here you see the door has been reinforced using steel. So aluminum will not have the same longevity as steel. Well, we already discussed the joints, the dry joints or the plug joints. Of course, they will not have the same resistance as welded steel joints. Here you see the gaps, huge gaps, and corrected or repaired by a steel flat. So that's pretty clear. When it comes to flexibility, also here steel scores much better. When it comes to bending forms and shapes, we can bend all the profiles that we have in the portfolio. In the catalogs, you will find the bending criteria, so the minimum bending criteria. The rule of thumb is the thinner the profile, the tighter you can bend it, the smaller the radius is. And these radii are smaller in general than the aluminum radii that you can achieve. That's why we can produce, as you see here, nicely bent facades, doors, and so on. I will show you yet another example of what's possible with steel. If you guys know the book from Agatha Christie, the house was actually built in my almost hometown. This is in Poland. A crazy architect decided to build this house from the book, and he used for that.
So an indication of what you can do with drugs.
Exactly, he was a vivid LSD user. So
yes, exactly.
And he made it. So as you see here, only the hinge profiles were straight. Otherwise, you would not be able to open the door. All other profiles were bent. So nice example what steel can do.
Crazy.
Mm-hmm. All right. This is it, really. I think this was some 13 reasons why steel offers more advantages when it's compared to aluminum, and why you have a very good material in your hands now. Any final questions?
Brilliant.
No, that's covered.
Excellent. Okay, then